Hello mathematicians, we're now going to start our next topic, which is the quadratic function. So much of this you already know, so parts of it will be a very quick revision. So we know that a quadratic function is written in this form, and what makes it a quadratic is that the highest power of x is 2. Now it may have a single power of x, or it may not, and it may or it may not have a constant, but it must have that highest power of 2. The graph of a quadratic function is a parabola. And when we write a quadratic equation, it's got the equal sign in it, and that will be ax squared plus bx plus c equals 0. And we know about how to solve those. We can either do it because we can use the product and sum method, or if we can't find those, we can use the quadratic formula. Or we can even use completing the square, which is essentially what the quadratic formula is. Now, regardless of how we do it, the solutions of a quadratic equation are sometimes called the zeros or the roots, and technically they are the zeros of the parabola. They're the points on the parabola where the parabola cuts through the x-axis. But these words are unfortunately almost used interchangeably at times. If we're going to sketch a parabola, there's a certain process that we follow. It's not strict, but in general, check the concavity. We know that if A is positive, it's concave up, smiley face. Find the y-intercept, which we just read off as the value of c. The axis of symmetry is minus b over 2a. Now there's a formula for that, which we spoke about previously, but there are other possibilities as well. And the zeros, the solutions to this equation here. So let's go and have a look at a parabola on GeoGebra and think about those things. So here we have the simplest quadratic, y equals x squared, and the simplest parabola, of course, as well. Its concavity is up, and if I change the value of a, then I'm changing, so this is the number in front of the x. The bigger that gets, then the tighter the parabola is to the axis. And when I take it down through here, the parabola opens out once it gets less than 1. When it equals 0, it's not a parabola anymore, it's just a straight line. And when it becomes negative, the concavity has changed. If I switch this back to somewhere near 1, so it's y equals 1.1 x squared. No, there we go. Now, what about c? So if c is added, my parabola slides up, and if it's subtracted, my parabola slides down. So again, if I take it back to there, the axis of symmetry is the y-axis in this case. And how do I move the parabola off having the y-axis as the axis of symmetry? Well, I introduce that linear term. So as I introduce a value of b, it does this odd combination effect. It moves it both off the axis and it moves it up and down as well. So if I do all of those, and if my computer would behave, then I can notice that in this case here, my parabola is cutting the axis at a couple of points. So these are the 2 points, these are the zeros. So in my equation, I might just see if I can make it a slightly nicer equation. X squared plus 2x, well we know we can cope with that. We could take x outside the brackets and have x plus 2, and we would get x equals minus 2 and x equals 0 as the roots. And if I throw in a c as well, then I can see that if I take it up too high, there are now no longer any zeros. If I drop it down here somewhere, then I'm going to get more zeros. So if we keep that in mind for later on. Okay, so let's look at a couple of these examples. We have to sketch the graph of the function showing all intercepts with the x-axis and the y-axis and the coordinates of the vertex. So if we look at this first one here, we can see it's a parabola which is concave up because it's plus x squared. If x equals 0, or x equals minus 4, the y value will be 0. So they're the points where we cut the axis. So our parabola looks something like that. So 0 and minus 4. Now the axis of symmetry, we could use our formula, minus b on 2a, if I multiplied this out. But I also know that it's midway between the two roots. So the x value is minus 2. And to get the y value, I put that up into my equation here. So that would be minus 2 multiplied by minus 2 plus 4, which is plus 2, which would give us y equals minus 4. Now for this one here, I'll just do it very quickly. We can see x equals plus 1 and minus 1 are the zeros. That means that the axis of symmetry is going to be the y-axis. So my minimum should occur on here, even though it doesn't look like it. Where will it occur? Well, the minimum will occur at x equals 0, midway between these two roots. And when x equals 0, this bracket will be minus 1 and this will be plus 1, so that will become minus 1. Now we also know that we can use our parabolas to help us to solve quadratic inequations by considering the graph of the equality and then noticing when the graph is either above the x-axis or below the x-axis. So we'll just do one of these examples here. So if we look at this quadratic just here, we can see it's a quadratic which is concave up. Now where will it cut the x-axis? So if we try to think of two numbers that multiply to minus 3 and add to minus 2, that would be x minus 3, x plus 1. So that's nice, we can do it without going to the quadratic formula. And in this case here, that means that at minus 1 and plus 3, we cut the axis. It's concave up. For what it's worth, it must be cutting there at minus 3, but we're not after a careful sketch here. What we're after is where this quadratic, which is also this quadratic, is less than or equal to 0. Now, this stuff here is the parabola that we've drawn. So it's the y values of this parabola. So it's saying where are these y values less than or equal to 0? And of course that's on this part of the curve down here. They're the y values which are less than or equal to 0. What are the x values which give us that part of the curve? The x values are the ones between here and here, and including that and that. So our solution to that quadratic inequality is that x has to be between minus 1 and 3. Now, last idea before we let you loose. If a quadratic has zeros, x equals alpha and x equals beta, so these are the points where we cut the x-axis, then these must have been the factors, x minus alpha and x minus beta. And that means that the equation must have this form, that y or f of x equals a multiplied by the factors, where a is simply the coefficient of x squared. If a is 1, we're said to have a monic quadratic, and we know that they are easier to factorise and to solve. So let's have a look at this question here. So it says the general form of a quadratic which has zeros 2 and 8, which means that it has roots of 2 and 8, is this factor, x minus 2, this factor, and an a because we don't know whether it's monic or not. So y equals a outside of x minus 2, x minus 8 is the family of parabolas which pass through those 2 points just there. We need one other clue to know which member of the family it could be. So if it has a y-intercept of minus 16, what does that mean? It means that it cuts the y-axis at minus 16. When does that happen? It happens when x equals 0. So we know that little fact. So we substitute into our equation now. So we get minus 16 equals a times 0 minus 2 and 0 minus 8. from which we can see that minus 16 equals a times plus 16, so a equals minus 1. So in fact the parabola, the quadratic, is minus 1 outside of those. We're not going to bother multiplying that out, but we can see that it's a parabola which is concave down. I'll do one more of these. So has vertex 5 minus 12, then that's just saying that when y is minus 12, x equals 5. So we substitute that in. Minus 12 equals a outside of 5 minus 2 and 5 minus 8. So minus 12 is minus 9a. A then must be plus 4 on 3. And again, that tells us that we've got a parabola which is concave up. And I could write it out fully if I put the 4 on 3 into here and multiplied it out. So you could try these questions in 8a, and remembering it has to be some combination of the facts that we've just looked at.